All right, everyone. Thank you for being here. Last talk of 44Con. So what is this going to be about? Well, IoT malware. Internet of Things malware got very, very trendy as thanks to Brian Krebs and OVH's 1.5 terabyte attack around last year, this time of the year. OVH described a botnet of around 150,000 cameras, so IoT type stuff, with an internet connectivity of 1 to 30 megabit per second. So the attack altogether culminated into a 1.5 terabyte per second attack. So this really is the major milestone around these kinds of threats in the last year. Before that, I used to be speaking about IoT as Internet of Things threat since 2014. Did a lot of malware analysis around that. So this talk is about sharing what we've learned and how we shifted our approach to hunt for these types of threats. The agenda is we'll explore the problem area. We'll see how collecting threats and that problem. We'll discuss the solution of collecting threats, which are honeypots. We'll then, after the honeypots, we have samples. Now, what are the problems and the lessons to be learned throughout reverse engineering of the samples we've analyzed, we've got? We'll explore data analysis problems. Then we'll see 3 cases of malware analysis done around IoT threats or embedded Linux threats if you want. We'll talk about the future and some takeaways. But first, just want to say that I love 44Con. It's my 2nd year. First year as a speaker. Thank you. And at 44Con, we met amazing people who have that British humor, which is unique. And with this, we asked for crazy things because, you know, we're Canadian. We don't really realize the impact of the jokes we do. So I had Steve find us some mercs around the Brexit. And so this is Philip, a colleague of mine, who slept on the I Love Nigel pillow. And the stuff we brought from 44Con is also making a killer at the office. Like the Make Security Great Again cap, everyone loves it. Even the salespeople, they put it on and they brag. The Brexit t-shirt that Philip is wearing right now, and of course the scotch we brought back. So who am I to talk about those kind of threats? Well, I'm a cybersecurity researcher at GoSecure, co-founder of MontreHack, which is kind of not really related, but something I want to plug. It's a hands-on security workshop. I did CTF 101 workshop on Wednesday. So this is all related to my passion of information security and challenges and such, and so on. I'm a vice president of training and organizer of the Hacker Jeopardy at NordSec. So NordSec is a largest on-site CTF in the world. 400 people who participates. It's in Montreal. I have a gift from NordSec for you guys. So after the talk, the first person who will ask a question will get a full badge of NordSec, the hardware badge we give everyone. And so this has 2 ARM chips, so it's a very flexible and very powerful badge. That's for you. I also spoke about malware at various places, including Black Hat Europe, Virus Bulletin, BotConf, DerbyCon, DEF CON, and so on. I used to do also development on network access control products and such. Anyway, the problem area we're going to cover tonight. Try to forget anything that you've heard about the fancy talks of IoT, like the Internet of Dongs, if you've seen it, because what I'm going to focus on is really what is the principal threat to the Internet's safety, which are devices that are a bit different than dildos. Yeah, wireless IoT dildos. So what I characterize as Internet of Things is, or we characterize, embedded system. So it must be a small CPU, memory, and low cost. It has to be networked. Otherwise, you know, it's not as damaging to the internet as a whole. So Bluetooth, Wi-Fi, or Ethernet, it generally runs Linux. Like most of the case, it runs Linux, and this is related to the cost issue from the vendors. And it has no user interface. So no UI is kind of important. Otherwise, you can do more investigative measures. We'll see that later. Where it gets really problematic is when you add on top of that, you expose Telnet or SSH. You have a full user LAN, so you don't have a restricted shell that is kind of a Cisco iOS shell, which doesn't let you run command, download binaries. But when you have a full user LAN, then you can do more damage, and it's easier for malware to infect it. It has global default credentials, so admin or admin D-link and stuff like that, as opposed to per device generated credentials. So if there's a way to get in on one and it's the same to get in on 10,000, then it's a problem, a bigger problem. It can be plugged directly on the internet, so this might be like by design, like an IP camera, for example, but it could be by mistake, like plugging a router upside down, like the WAN and the LAN mixed up. So this, you see this like when you scan the whole internet. And in addition, if it has benefits of being plugged on the internet, it generates a bigger problem. For example, DVR systems and IP cameras, home monitoring systems, people will tend to connect them on the internet to access them remotely, but they will do so badly, and they will be part of the problem. So no general purpose user interface. So of course, these devices have a web interface or a mobile interface, but or no interface at all. But this is not enough, because you need to investigate and go below and have access to the files, and you need a full interaction like a general purpose operating system does. So one does not simply investigate malware incidents without a user interface. It's an important point. There is no third-party software. So this is kind of a weird saying. There's no AV, but AV, I know it's not cool or trendy right now, but it is kind of important because it's the collection mechanism for the trends of malware or crimeware. This is how the industry gets access to those files and can see what people are doing and can have telemetry. And telemetry helps convince law enforcement that a problem or a group of criminal actors is important, is prevalent. So without all of this, we're more in the dark. But that doesn't mean I want AV on IoT stuff, doesn't mean that, but it is part of the problem or the new challenges we have to face. So malware investigation on IoT, because of these constraints, is different than desktop, mobile, or even server-side threats. On desktop and mobile, you bring the bad stuff in. It's users that attract the malware samples, if you want. On IoT, there's no UI, so the bad stuff needs to reach in via admin channels usually, and the bad stuff is not, no one realizes that there is bad stuff, As long as your device behaves, you don't even understand that you're infected. And as long as you have unlimited bandwidth at home, you will never notice, you will never know, even if you DDoS the shit out of everyone on the internet all day long. Server-side threats are kind of a bit different because IoT malware often infects server-side, like Linux servers that have weak credentials. Some of the IoT malware purposefully avoids x86 and x86-64, which means that some of the malware will not infect it, but most of it will. So our first problem that we want to describe is having access to binary samples. So what are the areas of, what are the ways that we could have access? So one of them is soldering on the UART and then having a shell on your router and then extracting files. One of the ways I did in the past is you find the file and you cannot download it because it's only a serial connection, but you put it inside the web directory of the web interface of the device, so you can download it from there. It's kind of hackish, but it works. But the problem is, soldering, it requires hardware and it doesn't scale. Also, it will not work well on well-hardened devices. So for instance, you want to investigate or attract ATM malware. If you purchase a real ATM on eBay, then there is a temper proofing that is done on these devices, and it's a lot harder for you to get to actually have a shell on those things. Another way is asking nicely for files. So this doesn't work either because people don't know they're infected, and extraction requires specialized knowledge. So you can do it, on your own, but convincing people like your mother to send you files on a router is another thing. So again, it doesn't scale. You can find a way in. So most malware gets in via telnet SSH, so you could reuse that channel, but it could be tampered with. So as soon as people or malware author would know that researchers would do that, They could then backdoor the SSH daemon to hide some processes from you and stuff like that. So usually you don't do an investigation at the same privilege level as the malware. You want to be at a higher privilege level so that the malware cannot lie to you. So this is a big caveat. But the other big problem is that it's illegal. You cannot go on and scan the whole internet and try admin saying, yes, it's because I want to see if it's infected. It doesn't work that way. You can hunt on VirusTotal. So VirusTotal is kind of the industry's big database of viruses. You upload a Yara rule, so kind of a fancy regex engine where you could try to match for specific architecture, binary files of specific architecture, which is what I've done, or I'm still doing. But the problem is it relies on individuals that are submitting files. You don't get the AV industry power of file aggregation because the AV have not visibility on these devices. And so what you have is just one-off samples once in a while and stuff that is kind of hard to reverse engineer or look at. And then after 1 hour and a half, you realize it's LS binary for ARM. You just lost an hour there. And there is still not a lot of results. So there's kind of a feedback loop problem. People don't hunt for these kind of threats there because there is no sample and people don't upload the samples that they've got there. So it's not working. So what we've been doing is we saw that collecting via honeypots worked. If you mimic the threat you are after, if you know a little bit about it. The problem is honeypots are complex. So honeypots, what are honeypots? Well, it's a system that is trying to lure attacker into showing how they operate, the attackers, including the files that they will drop, so TTPs, tool, tactics, and procedures. And then you pick a component and an architecture, and you deploy it. There's kind of two big ways to do IoT honeypots, and you can do a hardware one, so you can have routers exposed on the internet, put some tool in between, network tool, capture all the packets. But it comes with maintenance costs, and it needs effective monitoring because you will have real infected devices that could participate in DDoS attacks. So you need to react quickly if something happens. And of course, you cannot deploy it. If you want to see how the IoT threats in Russia are compared to those in Brazil, are compared to those in Europe, you cannot do that unless you are a big company and you have a lot of friends worldwide and you ship them hardware and you trust them to deploy them correctly. So it's kind of a limitation. The other approach, you can take a software-based approach. The emulation layer, of course, slows things down, but I mean, you're emulating small CPUs, doesn't matter. Can be fingerprinted. So fingerprint means that the malware group can write some code to try to identify or understand that it is in a honeypot. And you see a lot of these. So it becomes an arms race because you see what they looked at and then you realize they pull out. As soon as they found this file, they pull out. So you need to emulate this command or this file. And so it takes a while, but it's a problem that can be solvable. But some other systems, like if you are not running OpenSSH, a real OpenSSH, and they fingerprint the SSH layer, then sometimes you can be blind. You can never see what's going on and don't understand why. It's more flexible though, so you can deploy it in the cloud, you can shut it down, migrate, you can have it deployed at several geographic location. So it's more flexible and it's kind of cheaper because you don't need to buy the hardware and it requires less maintenance, so that makes it cheaper. Low interaction honeypots now compared to high interaction honeypots. So giving a full system would be a high interaction honeypot. A low interaction honeypot is a full emulation. Like there is no real binary commands that will be executed. So this requires less monitoring. So you have less chance of becoming part of the problem, spreading an infection, attacking other devices. And so this is what we've decided to go on. Doesn't give access to a real shell. So here's quickly the architecture of the honeypots that we've built and deployed worldwide. We still wanted to emulate some malware samples, so we added and redirected the traffic with firewall rules, but we have a QEMU running ARM on one side, which we put a HTTPS man-in-the-middle proxy in front to be able to see the plain text traffic. And on the other side, we use Cowrie, which is a low interaction honeypot that I'll talk about later, where we deploy, we mimic the targeted device and full BusyBox environment with Telnet in this case. We use IP tables to route the traffic, as I said earlier, and we use dumcat to take a full packet capture of the environment. So components we have is full packet capture, embedded architecture and userland. We use the Aurel's Debian images. He has MIPS and ARM and the two types of ARM images. For low interaction, we use Cowrie, and for the HTTPS man-in-the-middle, we use man-in-the-middle proxy, a Python tool. So Cowrie, it emulates the system of a target device. It has a tool to do that, so you can extract the content of a router, of a firmware, the file system. You put that tool inside the root of the file system, and it will gather all of the files and mimic the permissions and all of that stuff for you. And then this gives a serialized Python object, and you just load it when you do the emulation. So it's kind of flexible to emulate file systems. You can modify the output of commands. It's easy to patch. It's in Python. The Twisted framework, kind of relatively fun and fine to work on. But the problem at the time, it had no telnet. So lack of telnet support, we decided to fix it. So last August, I sent a pull request with basic telnet support implemented for the Cowrie project. And thanks to Michel, he merged it. And so we're kind of glad to say that everyone who studied Mirai using Cowrie, it was possible because we had this pull request sent at that time. The man-in-the-middle component, what we needed to do is to intercept SOX traffic. So one of our malware investigations had a heavy proxying pattern using SOX proxy. So we needed to inject firewall rules, redirect that to a process, and then be able to collect the plain text. What is good, I tried BetterCap first instead of man-in-the-middle proxy because a pen tester told me BetterCap is better. But it was crashy in my context because it's not made to run for months. So man-in-the-middle proxy has been really stable, and it has a library to parse the logs that you've get. So you can really do advanced querying and gather the stuff. If you have several honeypots, it's really useful. The full packet capture, I chose dumcat because it's more modern, but it uses pcapng format, which is more fragile and doesn't work with AOL's Moloch open source database of network traffic. So I mean, your millage may vary, but I've been able to fix most of the PCAPs that were corrupted using Xeditor, so it's not that big of a problem. Supports automatic rotation, and I really recommend to do it because otherwise you need a lot of memory in order to analyze the stuff, and you can parallelize a lot of the parsing or the extraction if you have several files. Use more cores on your server. And the strategy I've used is you move your SSH to a non-standard port and you don't capture it. So this way you avoid the problem of as soon as you rsync out your files, your PCAP files, and if you collect SSH, your PCAP will grow. There's kind of a feedback loop here that you need to avoid. This is just like stuff you will figure out doing it a few times. Full packet capture is always better than not having it because some operators will wget some files somewhere. But let's say your honeypot is prepared for that and will dump everything that is the target of a wget. That's good. But then some other operator will come and will exchange binary using echoes inline of the telnet connection, and then you're out of luck. If you don't have the proper logging on your server, on your honeypot, you will be out of that data. Now that we have samples, since we have honeypots deployed worldwide, now we have access to files. What are the reverse engineering problems? Well, the biggest problem is statically linked strip binaries. So statically linked means that the libraries are inlined into your executable, which makes the file big and makes the interface between the C library and the malware code blurred. It's unclear anymore. And this is a lot of code. Like I have example I'll show you later, but a lot of code to figure out. And if it's stripped, it's even worse. Because strip means there's no debugging symbols. So no method names, everything is just purely optimized assembly machine code. So this is really harder. I guess I said all of that already. So just to give you a sense, this is the Linux Moose binary. These are a few of the functions. So the only function that is identified is start. And on the screen, we see only 33 calls out of 500. So there's 500 subroutines in that binary. And there's only start that is identified. So all of this needs to be analyzed. Let's look at the kind of function that you will get to analyze. So this is with symbols, the printf family of functions. So only for a single printf somewhere in the code, you realize that you have like snprintf, sprintf, vfprintf, and then printf somewhere in there. And at the middle of there is vprintf internal. So this is a code that is inside the C library, not exposed. But this, without symbols, all of these graphs are individual functions. If we expand and look at the whole graph, this is it. So this is all functions that you would need to look into in order to understand that you are inside a printf family of function. Now let's say you open, you browse around the code and you open by accident without knowing vfprintf internal. All right? This is what the function looks like. This is the assembly level. We don't see, of course, the assembly because it's too zoomed out. But this is a shitload of code that is unclear because there is no variable. And in that code, there is not a single system call. So the only thing that you can map out and understand and go back into statically compiled strip code is the syscalls. So unless you are a very seasoned reverse engineer and you recognize the graph patterns, which is hard to do in that context because of different C libraries and different versions doing things differently, there's a little chance that you will figure out quickly that this is actually a printf code. The ecosystem of open source code makes it even worse for reverse engineers. You have GCC, GNU libc that are always changed, so the compiled binaries will always change based on that. There is little IDA flirt signatures, so the flirt signatures helps you identify functions automatically based on binary patterns. And there are various C libraries, so mulibc, eglibc, muzzle, glibc. It's very difficult. So what we tried to do at first is wrote an IDA script that would map the syscall of the Linux kernel and would tag these functions inside the code. The problem is the libc is too big and it has too much abstraction level. So even though we had a put syscall identify, put which is used in print, you would still be like 25 functions away from real malware code using printf, for example. It's too much code to RE. So what we found as a solution, it's actually a former colleague of mine, Marc Etienne's idea. We decided to reproduce the environment. So architecture, libc, compiler version, sometimes or oftentimes these are still in the strings of the binary. This will change eventually because a malware author will know and will strip them, but for now, so far so good. We build the libraries with symbols under the same conditions. This sounds easier than it actually is, but it's the way to go, so I mean, you need to figure that out. And then you use bindiff to map the library functions up to what you have in your sample. And then you can focus on malware code. So this is what we've done in the Linux Moose case. So this is the output of bindiff. What you have on the left-hand side is the unidentified function, the fifth column, and 2 column on the right. It's the name of the the thing you compiled with symbols. So what we have here is all 99% similarity, 99% confidence. So you can, after the fact, you can import all of these symbols into your IDA database, and then you can focus on malware code. This example, it was a UC libc with a specific version under the OpenWRT toolchain with the exact SVN revision that was stored in the compiler output. This really helped us. We mapped more than 225 functions with high confidence, high similarity. Other reverse engineering problems, it's that doing dynamic analysis, you need to match all of the environmental constraint of the target. So architecture, storage requirements, so NVRAM, for example, is complicated. And then shell access to the targeted platform. Right now, it's not that bad because there's no anti-debug techniques. There's no like, oh, I know QEMU doesn't support this instruction, so I will use it type of stuff because the malware author are still not aware of the kind of things we do to track them, but eventually things will get worse, as I said before. Then you have another problem. You have an important amount of data. You have PCAPs, you have log files that you've collected for months, that you distributed. Maybe you fetched it in all of it on a single server. So what we've been able to do is we figured that a solution on a centralized single server with IPython notebook running as a collaborative IDE on that server was the thing that worked best for us. So at some point, we reached the limits of the CSV reader of Python, and we switched to using scalable libraries like Pandas, NumPy, and SciPy. Pandas CSV ingester is insanely fast compared to the native Python one. But even then, we would have problems with parsing, 400 gigabytes of PCAPs. So we parallelized those heavy CPU and I/O tasks using GNU Parallel. So GNU Parallel is kind of Xarg on cocaine. You give it a thing, it will evaluate how much core you have and will by default maximize your core usage. So it's very easy to use and powerful. We use specific tools for specific types of data, like T-Shark for PCAPs and mitmproxy for the mitmproxy logs. So now that we have our whole pipeline set up, what kind of stories do we have to explore using that all we've covered so far? First, I want to talk about LizardSquad guys. So it's GAFGit malware, which is actually GayFag, but the AV industry switched the letters because GayFag was too offensive. But this was a string found in the malware samples. So the LizardSquad, who are those LizardSquad people? Well, this is their famous Twitter logo. It's a black hat hacking group, mostly kids. They were big in the distributed denial of service. They even have a DDoS for hire service called Lizard Stressor. They are the one who DDoS the PlayStation Network and Xbox Live on Christmas Day in 2014. A lot of people remember that. Kids especially, or gamers. They were probably under a study by the law enforcement at that point, but when things escalated is when they started doing bomb threats. So the kind of bomb threats that they did is they said that the Sony vice president of the gaming division carried a bomb. So they do anonymous calls, say that this guy carries a bomb. They landed the plane like urgently. They arrested the guy. They took the anonymous complaint seriously. And so after they realized they were played, law enforcement was probably really pissed, and then several of them were arrested in 2016. But the malware source code leaked, so it's still very prevalent. There is a lot of different modification of the code, but we'll see that later. So after what I described, those guys are kind of cyber rascals, little assholes that you want to, want their mom to, show them respect. So Lizard Stressor, turns out it was running on a hacked home router. So this is, Krebs confirmed that this was an IoT botnet if you want. But in fact, the malware can affect servers also because they have an x86 and 64-bit variant. The various names, monikers on those, under what you can find these samples is Powbot, Hydra, Katan, all of the fork of Katan have different names, and probably a ton of other. So what does it have? It has a telnet scanner, does flooding through UDP, TCP, junk and hold techniques I'm not even familiar with. It supports multiple architecture, including Super H. Now, I don't know of any Super H device exposed on the internet, but I'm pretty sure they just decided to compile all of the architecture that their code would compile under and just, use that. I found a leak of the server-side source code, and they added this nice comment on it. So they were aware of their IoT capacity, like this version now with refrigerator support. It's kind of little bastards. The attack vectors that they use, as I said, telnet before, but some variants have Shellshock support, and others do support SSH. Of course, bundling in SSH requires linkage to OpenSSL and makes the malware a lot bigger, but still you can find some of that. They brute force with a short list of weak username and passwords. This is an example of the Shellshock attempt. So it would pass the famous Shellshock bug, like the empty function and then environment, user agent environment that is turned into an environment variable because of the CGI. Then it would do a wget on a script piped to a shell, and that's it. This would, again, wget other code and then start the execution. Some of the variants I stumbled upon and analyzed had HTTPS support, and some even had Cloudflare protection bypass. So Cloudflare protection is a JavaScript puzzle that your browser is able to solve because it has a full JavaScript environment. But when you're a DDoS malware, little, no JavaScript emulation possible. So what they did is they implemented in C a solver for the specific Cloudflare challenge. So on the left-hand side, you see the Cloudflare Nginx string, so matching that string to enter the brute forcing function. And on the right-hand side, it's an overview of what they had to implement in order to brute force or not brute force, solve the Cloudflare challenge, JavaScript challenge. So it's kind of fancy. Pretty sure it's not the kids who wrote that code. So is it sophisticated? Well, Lizard Stressor service database was leaked, and all of the username and passwords were in plain text. So no hashing at all in their service. So I mean, maybe they didn't know what they were doing much. The IRC Command and Control exposed the number of users on the channels, so I could know, this botnet has 2,000 infected hosts. And the botmaster's nickname were kind of revealing and, you know, not that obfuscated. So I watched for a few days who they were targeting, because they would send the targets as command inside the IRC channel. And it was mostly gamer-related targets for this botnet. So DSL lines of consumer ISPs and game hosting companies. I saw some Blizzard and some EVE Online kind of like Whois were mapped to those IP address would map to those domain IP owner. So it's kind of, anyway, it's kind of funny, gamers. So this malware, because the source was leaked, is very prevalent, and now it's beyond LizardSquad. You know, a lot of kids, I have the impression, or a lot of people can, you know, operate a botnet based on these. The thing is, you fight a lot on an infected machine like that. You need to implement a kill list, otherwise someone else will get on the same device as you, kick you out. So there's kind of a constant war going on inside the infected IoT online. Another thing I want to talk about, the second campaign, is Linux Moose. So I've been talking about Linux Moose for a while now, 3 years. But last year at Black Hat Europe, we released a big study about the way the botnet is used. So kind of a higher level analysis, and we realized that it's selling fraudulent followers on Instagram mostly, Twitter, YouTube, and other social networks. We analyzed the price structure. We analyzed a lot of that. I encourage you to read that paper. But the first big paper I did, which was more the reverse engineering focus, was in 2015. This is the kind of the attack we did to understand the kind of traffic, because social network traffic is always HTTPS. So we needed to go back to HTTP, which is related to the manipulatable proxy tool I talked to you about earlier. But of course, we didn't break HTTPS. You know, this thing is solid. But what happened is we weakened a portion of it. So in lightish purple, you can see that this HTTPS traffic is not authenticated. So a normal user would get certificate errors. What I did here is I mimicked the certificate names of security appliances. So I put in certificate names like Fortinet or Checkpoint or, you know, WebSense and stuff like that, hoping that if a user, an operator would see it, they would say, oh, it sounds legit, and accept the certs. But what happened actually is nothing changed. They didn't even notice. So they disabled certificate checking inside their own, you know, code that would be doing that kind of malicious traffic. So with this, we were able to unveil a lot about that botnet. So it's a profitable botnet that advertises its services on the internet, normal internet. and selling them to normal people. So they can charge people with legitimate credit cards and say, we will add followers to your account, and they have no money laundering to do. Like, this is way cooler for them than, you know, Bitcoin mining or stuff like that. You know, they have nothing to do. And they can probably tell like their cousin and their family, like, oh yeah, I'm in social marketing. And everyone's like, oh yeah, social marketing, there's a lot of money to be made on that. I understand why you have a Lamborghini. So I mean, this is just crazy. We've tried to get law enforcement attention on this problem, but the thing is, the botnet is well done, so I have no numbers on infection. And it would be technically possible, but I would need control to IP addresses of entities that don't collaborate. So it's kind of a fun / sad story here. But the big way to summarize this, this operation is that they are stealthy. They don't do anything on x86. So they don't infect any server. It's only IoT devices. They're adapting because they were taken down and then they changed their code and they switched the protocol as soon as we published about it. And now, after a Black Hat Europe talk, they took down the CNC again, and now I'm still trying to find where the new CNC are and trying to get infected. But I will need to build a new honeypot because it will probably fingerprint mine. They do no direct victims, so the victims are only people who are fooled by the fake fame. So let's say I'm a model and I want to have better contracts. I buy 10,000 followers, you know. The victim here is the person thinking, hey, she has a lot of followers, I'll hire her. So it's very indirect victimization here. The social network don't really care, you know, they do big sweeps. So Instagram, every 2 months, they will like find something with their machine learning that these are fake accounts and then just remove them in bulk. We buy some followers through that operator and we figure that out. It's in the report or a blog post, I don't remember. So they're hiding in plain sight. As I said, they can, you know, sell this on the clear web and declare taxes on that money, and no one will ever, you know, do anything about it. And they make money. The numbers in our paper are big, but we realize now that there is a reseller model. So think that for example, if you have a 20,000 botnet, you make $250,000 per month doing that, US dollars. But the thing is, we thought it was alone, but now we know that there is a reseller model, so it's less people making that amount of money, but it is still a lot of money. So our latest analysis, it's called Chaos. So we found a logo on it on the internet, but it's not the official logo, I think. The intern just put Chaos in Google image and took the first thing. That makes sense. So how we got Chaos? Well, SSH credential brute forcing, this time from Tor IP addresses, so a bit cleverer than the others. What it does first when it connects is it wipes history so that you don't have any access to anything, which is kind of usual, but I decided to include it in this analysis. Have I skipped a slide? I had a high-level overview, but I guess I removed it. It checks SSHD binary for competing backdoors. So this is not honeypot fingerprinting. This is like, oh, I know that some backdoors put IP and port in the backdoor, so I want to find it. I grep for backdoor inside SSHD, and I look for places that I know are storing stolen credentials usually. So these include things is other SSHD backdoors that store credentials at these locations. And they cat it, so this way they can collect them, steal it from the infected machine. Because this is done through like an interactive session with the server. And then they wget the backdoor, and they run an install script. They remove the file that they got, and they run an install script. The backdoor is a raw socket backdoor. So what that means is that it checks every packet that comes on the host, anything, so no matter what port or whatever. And if it matches, like you see in that screenshot, if it matches a certain password using a crypt with a small salt, so standard Unix crypt, small salt, and then the password, which is obfuscated in the binary, but we could crack in like 5 minutes on our cracking rig. If it checks out, then it will do a connect back on the source of the connection. So it's a connect backdoor using raw socket for activation. It's kind of clever because let's say you have your server only exposes SSH and HTTP, and you already have services running there. So you couldn't add another backdoor if it's properly firewalled. You couldn't add another backdoor because of these. It would be firewalled on every other port. But these services, since they are already used, you cannot open 2 listening sockets on the same on actively used port. But since it's a raw socket one, it doesn't matter. You can listen to SSH traffic, listen to HTTP traffic, and if you get the right handshake, do your connect back. And since outgoing ports are rarely filtered, this would work. Also, another interesting characteristic of using raw sockets is that it doesn't show up on a regular netstat-an, which is what people do when they think there's something fishy going on. Okay, I'll look at what is exposed and stuff. And this doesn't show up. You need to put a -w to show only raw sockets that are activated. Then it would be really obvious, you know, because usually you don't have raw socket listeners. So this is quickly the handshake, if you want, of the backdoor. So you send to any port with the password crypted with a hard-coded salt. Password is checked. Connect back on 8338 port. Then they generate a key, shared key. So this backdoor is, the network traffic is encrypted and HMAC'd. So the key generation happens on the client side, and then the pre-key material is sent. They have the same data, so they can generate the same key, and they use 2 keys that they swap for encryption and decryption. Quickly, the packets are like that. So there's a 2-byte size, then a payload of a variable length, and 3 zeros at the end, 3 bytes of zeros. This is the marker, so that knows when to stop. And then a sequence number and the HMAC. The packet integrity is done as you see below, so the 3 zeros are used inside the concatenation, and this allows the other side to detect if they were tampered or anything. And the use of a sequence number is to prevent replay attacks. It's kind of clever and interesting, but since the pre-shared key is shared and sent in plain text, you could write a decryptor for that stuff. So it's kind of clever, obfuscated, and you know, if you have simple plain text rules on your network traffic, you will not see it, but nothing more than that. We will release a blog post about it early next week. I wanted to do it this week, but with the workshop and with this talk, I couldn't like manage to get it out on time, but it's like almost all written. It will be the first piece of our intern from Germany, and I think it will be interesting. And we're still working on that operation. With the chaos backdoor comes an IRC bot. We have been unpacking and analyzing the IRC bot, and we have found like mining and stuff in that area, so we'll eventually publish about that too. So some future work I want to do regarding hunting these types of malware. I would like to be able to execute the dropper. So what we've started seeing is in a honeypot, you get a small binary, which is which will just do a download and execute. And because it's a binary in the honeypot, it doesn't work. So I would like to use QEMU binfmt to be able to run certain pieces of code and maybe seccomp to filter out what I would allow for syscalls in order to collect those stage 2 samples. Because if you're not fast enough, the download will not work and stuff. So that would be a really a big improvement on collection. I want to emulate more type of devices and larger devices. I tried SCADA stuff, but it's very complicated, and I didn't collect. I just saw, you know, poor guys that didn't know what they were doing, and obviously I wasn't, so I decided let's emulate other stuff. And I would like to harden the possibility of fingerprinting the honeypots, because we need to work on that. I have a blog post coming up on how to do device emulation with Cowrie, so full instruction. You take a firmware, you bin walk it, you extract it, you copy the file system and all that. It's like written, 3/4 written, so it should be in October, it should be out. On the data analysis side, I would like to improve visualization and do a elk stack deployment or maybe Graylog. And once done, I want to share the collector and the code because I mean there's no value in not sharing stuff like that. For PCAP, I tried already AOL's Moloch, but it didn't quite fit what I was looking to do. But I need to give it another try. And I want to also build a higher level construct around IPython's parallelization API based on this type of analysis, so focused on PCAP parsing and stuff like that, so that it's easier for people to get into the large-scale data analysis in that context. For reverse engineering, I would like to build IDA flirt signature for more embedded devices architectures and C libraries. I've been saying this for a year now. Maybe someone done it, so I need to really look on the internet if there's something. And if you're aware of anything in that regard, please let me know. Now, fixing the actual problem. Last stretch. Device vendors, they should stop using default credential and use per device credentials instead. So they're already doing that for the WPA keys and routers. So why they can't just adapt that process and put it to the admin thing? And this would get rid of a lot of problems. And I mean, you print the admin password on the thing. This is not a real attack surface for someone, except maybe your own kids if you put some internet time management on your router. But then just scratch that password or change the password, For the layman, you really need to get rid of the admin stuff exposed by default. So this leads to the second point, stop exposing general purpose management port. Leverage the fact that you have a physical device. Like, okay, management port, if you push a button, it's live for 5 minutes. Something like that would really work better. And again, make it the default, but for people who have larger systems, make it optional that the telnet and SSH can be exposed. I understand that if you deploy a D-Link network at work, you want to do remote management, but you will not have default credentials, right? Consumer should put password on your devices. And I would even say that people, when you are at some friend's house, you should try 192.168.11 admin. If you get in, change the password, put it on a post-it, and just never tell the person. I have a demo. So that's it. I mean, this would work. Like, even if the pass is weak, and the person who wants to manage their device, if it was still the default, they'd never realized. And if it doesn't work, they will try 3 times, it will not work. They will go see the actual thing to reboot it, and then they will see your post-it. So now, advice for developers: have a hacker mindset when developing features. So anything that can be done at scale will be abused. So think about that. You need to really think about abuse cases and have a hacker mindset, or have someone else audit your stuff, and think to leverage the implied physical access. So if something could be abused, then just ask the user to push a button, and it will not be internet scale abused, So takeaways. IoT is insecure, yes, but it can be fixed for the low-hanging fruit problems of every malware analysis I've done. So there was like a bit of Shellshock, and that's it. Everything else is weak credentials. And so we need to continue actively collecting and analyzing samples to know in advance what's coming next. Do we have any questions? And before people think about the question, thanks 44Con staff and volunteers for the opportunity. I really, really enjoyed it, and I love this conference. Thank you. Yeah.